So, as promised, today I'm going to talk about this autonomous mobile robot for roll-to-roll inspection line. So what's a roll-to-roll inspection? So basically, we have a bunch of products that has been rolled into a cylinder. They are flexible printed circuits, basically soft membranes with circuits on top. And nowadays, there are so many flexible printed circuits in our electronic system. Like you have foldable cell phone. There must be some circuits on the screen that could be folded. It's flexible. So it's very common technology nowadays. And this company, they have those rolls of circuits, but they need to make sure the quality of the circuits were made properly. So they need to put this entire roll of the circuit into a machine, inspection machine. So a human worker will be taking one edge of the roll and then insert into some kind of feeder. The feeder will be taking the roll and start to move from one edge along the entire roll, and there are cameras taking pictures to figure out the quality of every circuit on the roll. And the feed will be, once some portion of the roll has been completed, it will be rolled back to a different roll. So when the original roll finishes, they at the end ends up all the entire roll goes to the other. Okay. So this roll of flexible printed circuits sometimes could be quite heavy. Sometimes it's like 10 kilogram. Sorry. And it could be up to. They told me it could be as heavy as 50 kilograms. So imagine the workers in the factory. There are female and male. If it's a female or a very skinny female worker, it will be difficult for her to handle this, to carry this roll and then move it to the inspection machine. So usually they need more than two people, more than one person to carry the roll and then bring it to the machine. So our job was to have a robot system and then carry those rolls, put it into the inspection machine. Okay, so at the bottom of this system, the frame is made of metal. It's very heavy metal. So there are so-called Magnum wheels being installed at the very bottom layer of the structure. So one thing that you guys can work on is the shaft that carries. As you can see, we are going to accumulate a lot of different components on top later on. All the weights is going to be carried by 4 shafts. So the shaft will be bending. Okay? If the shaft is not strong enough, one day you will have yielding. So the design of the shaft is one part that you can work on. This is just animations about the Magnum wheels. Because of those rollers, there are some rollers surrounding the entire wheel, and they are being installed in some kind of diagonal direction. So whenever this wheel is rotating on the floor, it not only generates forces along the wheel direction, it also generates like a transverse force on the floor. So if you can mix and match different rotations of 4 wheels, basically you can spin the wheels separately. With different matches, the vehicle is able to move around forward, backward, left and right, and even move like a diagonally, or even spin at the same position. So this is what I mentioned earlier. So we don't see this kind of wheel for our daily life cars, because those rollers are usually made of polymer. So if it could be damaged quite easily if you drive this kind of vehicle on our daily lives road, on the street. It could be damaged so easily because we have small rocks and sand on the road. So usually this kind of Magnum wheel is utilized inside indoor with really flat ground. Okay, so what's on top? The entire vehicle carries several different things. A very large battery right here, very strong power supply, and you can tell we have really strong steel frames. You guys know about Guai? Do you know what is Guai? Oh, okay. Foreigners don't know. Let me tell you the story about Guai. Have you seen this? Foreigners, you guys know this, right? But do you know what this is for? It's usually, this brand of this particular flavor is a coconut flavor, butter coconut. And it tastes like puff, right? But every company buys this not for eating. They put it on top of all kinds of machine. Why? Because the brand name is so guai, this character, guai. Guai is the opposite of naughty. Being nice, be like a good boy, be like a good person. So I don't know why when they have this this brand name, I guess it's for kids. So there's a funny character right there, and maybe you can feed this to your kid, so they become a nice boy, right? So that was the original purpose, I guess. And this flavor is the most popular flavor because people buy this and put it on top of their computer, their robot. They want the computer and robot to be nice. Don't do something stupid and shut down on me. And also, it's like a green light. So in Taiwan, most of the machine, actually around the world, most of the machine has like operation light. Green light means everything's okay. And sometimes there's a warning, there's a yellow light or a red light, right? They want the machine to be green light all the time. So they buy this particular flavor of cookie. It's not cookie, it's like a puff. And put it on top of the machine. So I guess this is very Taiwanese. You don't even know this in China or any other Chinese cultural countries. Because Guai Guai probably is only sold in Taiwan. So this is a Guai Guai. So don't feel weird if in the future you see some really technical pictures about something, but you have a bag of snack on top of that machine. Okay, that was yeah. Anyway, from here you can see how heavy the whole vehicle is. Right now, at the bottom, it's 164 kilogram. Yeah, that's okay. Is this? Let me see which part is this one. Okay, this is the mechanism on the top. I should show you this one first. So whatever that is on the top is made of multiple, like a screw system and also motors. The purpose of this mechanism is to be able to move this platform horizontally, steadily, up and down. And because this plate is quite large, you need to kind of synchronize the motion of every screw everywhere. So my student designed this. We will talk about the screw, ball screw, for carrying loads. Not like the bolts and nuts. Similar geometry, but bolts are the threads that you usually fix something, right? Those are small ones, small bolts. But those are large ones. Similar geometry, similar mathematics for calculating the stress inside this geometry, but different purpose. Bolts and nuts usually are used for getting metal or different materials together. It's a different choice of glue. And here is the use of screws are used for carrying the loads. Okay, it has the ability to carry loads, and it's easy to operate because when you spin the screw, you have thread inside the geometry. The geometry has to move along the screw. So by spinning, you can allow this platform to move up or down. Okay? And the thread inside the bowl can carry really heavy loads. So whatever that is shown here is weighing 70 kilograms. So in total, that entire system is like a 200 kilogram, 200 more. We do have a gearbox. The color is not clear enough. We have a gearbox to reduce the velocity. Because motor usually spins really fast. So we have a gearbox to reduce the spinning velocity. So this won't be moving too fast. And also when you reduce the velocity, you can increase the torque. Here, I think this is like a disassembly of all the parts for that mechanism. Okay. Yeah. I think oops. This is not a good one. Okay. So these are the details about the ball screws, gearbox, and some components at the upper part of the system. You can choose any components here for your final project. You can, for example, if you want to focus on one particular ball screw right here and use simulation tools, for example, ANSYS, to figure out what's the stress distribution inside, and then match with what you learned from the course, and also search for some more information from the literature, or you can borrow the thick textbook from me and check on some pages about the ball screw. And then you can try to match whatever you found from the simulation and then match with whatever you see in the book or from the information. And then figure out how well the design was. Was that selection a proper one? Is it over-designed or under-designed? How much life do you expect this ball screw can last? Okay, so things like that. You can focus on one part. Or you want to study more. For example, the entire driving system. The motor here, there's gear inside, and there's another gear here. And also, we will talk about gears. So you will learn what's inside gears. So there are several things that you can work on. I don't want to assign, hey, you work on this, you work on that. I want you to be able to freely understand what's important or freely choose what you are more interested in. Later on, this PowerPoint could be given to you guys. So you can later on spend more time on this PowerPoint and figure out what is more interesting to you. So my students did some finite element analysis already. They studied about Mises stress. But this time they study on the plates, okay? So I'm not sure if they study safety factor. This is finite element, maximum principal stress, total displacement. Okay, so from here you can tell basically deflection. It bended a little because of some weights somewhere. Okay. This is one of the structure. So I think they did finite element here and there, but didn't truly analyze. They didn't study safety factor. They didn't compare the stress with the material property. Not yet, right? This is auto display too. Oh, safety factor. Too safe. 82. Way too safe. So this robot is way too bulky. Safety factors 7 and 8. Very, very super safe. So that means this robot probably won't be broken in your life. You know, because it's, or you can, on the other hand, this robot can carry more loads. I believe they analyze this under certain load condition. But when you have greater loads, safety factor drops, right? So that means this system has a higher capacity for carrying loads. Okay, so those are the things that you can work on. But I feel like they didn't want it to redesign. They have no time to redesign, but you guys can. You guys can have some improvement in your computer design, and then reanalyze your new design and figure out whether it would be a better choice. For example, if I'm the boss, I will ask my employee, how come you design such a system that is super safe? Then you're wasting money, because you could have reduced the size of some of the components so that the total weight drops, the strength drops, and the safety factor drops, and of course the cost drops. As a boss, I would like to reduce the cost. Save enough is good. Enough is good. You don't need to over-design it. Okay? But when you say enough, it doesn't mean I want a design that is so close to the limit. I still need some safety level. So what kind of safety factor is appropriate? Maybe 3 is enough. Then 7 is over-designed. 82 is super over-designed. Okay. For the rest are things about the control system in this vehicle. So it's not super related to this course, but if you are interested, I will spend a little time on this. Basically, they separate the entire system into 2 chunks. For this chunk, they have SLAM, means simultaneous localization and mapping. So it's like you map yourself, you localize yourself and update the map. So SLAM is not slam dunk. SLAM is a known technology for indoor positioning. So nowadays, most of the robots which moves inside an environment, they need to figure out where they are inside the room. For example, the vacuum machine that moves on the floor, cleans the floor automatically for you. Usually they have SLAM inside. Because when it's moving, how does the vacuum machine know where it is inside the room? And usually the vacuum machine can move around without any cable, but being able to coming back home to recharge itself. So how does it know where it is? There are sensors inside. So the sensors inside figure out where it is. And usually, at the first time when you buy a vacuum machine, you install the system on the next to the wall, usually against the wall, turn it on, and usually the machine will have some kind of routine that moves around the entire indoor environment. This system will bump to the wall multiple times everywhere. That purpose was to build a map. So there's usually a digital map about the shape of your house. You never need to specify the shape of your house to the system. It basically builds a map by itself. So usually for the first couple times, that vacuum machine is trying to build the map of the house. And it's okay if you sometimes move that home to a different place. Of course, for the system, they don't want you to move it, or they don't want you to move the table or desk here and there, because whatever change you do, that will not match to the digital map it just got earlier. But it's okay. At your home, as a user, I will randomize the decoration of my house. So whenever that happens, the machine, of course, initially will assume the digital map didn't change, and it will keep on continue its routine. And at some moment, you will realize, hey, how come the wall changed its position, or how come this table changes its position? So whenever there's a change, you realize there's a change, it will update the digital map. That's why SLAM has a mapping. Mapping is like updating the map. Okay, so simultaneously localize yourself and update the map. So that's why the algorithm is called SLAM. So yeah, localization and mapping together is SLAM. We do have two levels of positioning. Usually, for our system, when we localize ourselves, it's based on some kind of laser measurement. So it's called the LiDAR. LIDAR. I don't remember what's the full name. LiDAR. I'm sorry. Let me check what's the full name of LiDAR. I don't remember. Laser something. Light detection and ranging. Okay. So basically, there's what's inside a LiDAR. Usually it's like a cylindrical shape. The sensor is having a cylindrical shape, and there's a beam of laser. Okay, and then this cylindrical geometry spins. So this laser will be emitting from the source, hit the wall, and then come back. So we have a receptor that detects how long the laser flies out and comes back for distance measurement. So usually you are able to take measurements like these because this is spinning. Okay? So if you can take distance measurement from the center of LiDAR and from the center and then to the wall, somewhere on the wall, you kind of have the geometry of the inner environment. And that's how you can build a map. So we do have that LiDAR system, and we use it for localizing and mapping. But the measurement is not accurate enough. So usually there is an error of maybe 10 centimeters, which means if you say, if the robot is having a distance of 30 centimeter against the wall, the measurement could be like 30 plus and minus 10. So the positioning error is quite large. So we need a second level of positioning. Over here we use camera. Camera is more accurate. So the purpose of these are like, we use LiDAR to position ourselves, have a rough position, and then we move close to the inspection system. Then we use a camera to capture certain landmarks on the inspection system to realize what's the true position of ourselves. Then we have slight movements to have good alignments. Then we can deliver the product that we carry and then send into the machine. So this is the mechatronics for the system. I guess I don't want to spend too much time. Okay. So basically a bunch of systems, mechatronics and cables. Anyway, this is more important, the video. Oh, what? Is that moving? Oh, sorry. I got it. Because it was in PowerPoint. And that jumps into the YouTube. So I should. So at first, the entire vehicle was moving. When it's close enough, the mechanism on top moves. We don't want the vehicle to be too close to the inspection machine because indoor positioning is not too accurate. And the mechanism right here were the ones that we built on the upper layer. Okay. I'm not sure what she's doing. Maybe just demonstrating. I mean, the robot, there's a gripper. The gripper release. Okay, yeah. Okay, so that was the video. Oh, there's another one. Let's see. I think they want to take it away, I guess. Yeah. So from this one, you can see everything more clearly. They have a gripper. So they didn't grasp from the outside because, you know, for all the flexible circuits are surrounding the cylinder. It's outside, and we cannot damage the circuits. You can only expand the claw and try to hold the hollow region of this cylinder and then take it away by expanding your fingers. So when we take a trip to E3, we will physically see this machine made by the students. Okay, that was it. Okay, so that's the end. In this particular project, I told you yesterday, there are 3 things that you can work on. Whatever shaft that you are interested inside this entire system, you can work on it, or whatever screw, or whatever gear. And in the entire system, at the bottom, we have shaft with a motor assembled with the shaft. Okay, so that shaft is something you can work on. And also at the upper part, we have a platform assembled on 4 screws. Those screws could be the parts that you work on, or any components that is connected to it. Okay. So, if, for example, if you are interested in this particular screw, there is a geometry that has a thread inside that is assembled to the plate. So when when this component moves up and down, it carries the plate. So the plate is like this, and you know the weight of the plate could be concentrating somewhere outside of the central axis. So it's actually generating some kind of moment applied to the entire screw. Okay, and we will never use single concentrated loads between the thread and the part right here. Usually we have a greater area, so it's a distributed load. Distributed load applied everywhere here. Because if you have a very thin plate and you have concentrated load applied to the structure, then over there you could have very strong shear force, right? The shear diagram would look like this, right? If you view the whole thing vertically, then you have very strong shear force, right, at one point. We don't want to see that. That's why usually you want a larger contact area. But if this area is too large, it will affect the range of your motion. You have smaller space for movement. Then you need to build this whole thing taller. If this is taller, then the whole thing becomes heavier. So everything is a trade-off. If you want this to be good, then something else will be bad. Okay? And on the top, you have loads vertically, horizontally. You have loads vertically, horizontally. Right? So this thread, in fact, could be bended in a certain way, maybe like this. Right? So we want to analyze whether this thread is strong enough. Do we need to buy a larger thread, or actually it's too strong? You can use a thinner one. To, whatever you buy, whatever mechanical component you buy, usually larger the more expensive, because it requires more material. Right? Okay. Now, later on, when I introduce about the lecture of threads, of screws, we actually study the profile of the thread. And the loads are, the weights are applied to the tilted surface of the thread. This is like a thread. If you understand what I'm drawing. So it actually have some kind of a stress applied to this area, and you know, the thread could be broken if the load is too large. So not only for the screw, we need to care about entire shaft, we also need to care about the thread, the strength of the thread. Okay, so that's if you are interested in threads. And right here we have a gearbox. Not this one. There's another system. There's a gearbox. We do have so-called bevel gears. Bevel gears are the gears that looks like an umbrella. Bevel gears. Bevel gears are the gears that allows you to change the direction of your driving axis. Let's say you have a motor at the bottom, you drive the gear, you drive the shaft right here, it's spinning in this particular surface or about this vertical axis. Because of the geometry that looks like an umbrella, has another cone shape of the bevel gear on the other side. These two cone shapes are conjugating with each other. So this cone spins, the other cone spins as well. So if you have a motor here, this is driving, then the driven gear will be spinning as well, but spinning about a different central axis. So this is the mechanism that allows you to change the rotational axis from one to the other. Okay, bevel gears. So we do have bevel gears in the gearbox. Later on, you will be talking more to my graduate student to learn more about what were the parts she used. And then with the information provided by them, you could make new suggestions. Like this is the motor and the decelerator, and I believe there's a bevel gear right here. So I think there are actually 3 bevel gears, if I'm right. And the motor spins right here. That driving force will be transferred to transferred to this horizontal bar. It will spin simultaneously with the motor, and also the thread on the top will spin as well. So one motor drives one thread and 2 threads. So it will move the platform. Is it for the platform movement? Yes, it's actually the true force for platform movement. She used 2 threads, these 2, to truly drive the platform up, to move the platform up. So the other, they are not threads. The other 4 are not threads. These are just, linear bushings. They're like a linear guides. So it allows this platform to move vertically only. It doesn't tilt too much. So I'm sorry. The only 2 screws are the ones that was connected to the gear, not the 4 vertical columns. The 4 vertical columns are linear guides. Okay, you just have bushing here with some oil inside, so it moves really smoothly up and down, but it doesn't stop you. It only holds you and allows movement along the vertical direction only. So this platform, it can only move up and down, constrained by these 4 linear guiding system. But the screw pushes the entire platform up and down. Okay, so as mentioned earlier, we need to focus on those 3 parts. Just double checking. Yes, you can analyze the shaft or the structure. For example, my student found the safety factor of the structure was super high, up to 80, too high. You can reduce the structure. If you want to reduce the structure, we do have softwares that help you to have topological design. So if that's something you are interested in, or the gear system that allows you to change the direction of your rotation, or the threads. Okay, so I think there are 4 parts that you can work on. You can choose either one: shaft, body. The shaft, the body, basically the geometries, or the screw or the gear. You can choose either one from them, or you can combine. Because the screw connects to the gear. The screw connects to the gear. You want to treat it as a whole system. You want to analyze them maybe separately and also as a whole together. You are free to do so. Okay, if you can analyze more. So those are the 4 things that you can be focusing on. Okay, you can either see how safe each part is, or you can suggest dimensional change. I think especially for the body, our frame was too strong. Where if you want to reduce the frame, then what would you do? Okay, so those are the things that you can work on. So from now on, after the exams, you need to spend more time on these. And my 2 graduate students will be helping you. So later on, when they propose, I think before they propose, they would like to know more about the design. Please guide them to have discussion with Janice and Aria. Because they are the designer, so they can. You guys need to think about, okay, whatever that you are interested, and you need to bring important questions to my graduate students. Ask them, okay, I'm working on the screw. Where did you buy the screw? What's the geometry? What item number that you use? Why did you do it? Did you study the allowable stress for this and that. So they have experiences of designing this, and it works. I know it works because it's super safe. And I know it's definitely overly designed. It's too safe. So your job is to analyze the parts inside, see if you can reduce the cost. Okay, but you don't truly need to make one. If you want, you can make a smaller one by simple mechanical parts, plastic parts, 3D printing parts. You can do that. Our lab will provide enough resources for you to build a small one if you want. Okay, so it's a very open project. You can choose whatever you want to do, but the entire scope is surrounding this particular vehicle. Okay, that's it for today. Thank you. I think we need to check the attendance.
Oh.
Okay, so there are two QR codes. The one on the, oh sorry, it's not showing. The one on the right is for attendance. The one on the left is to check whether you want to go to E-Tree with us. Okay, for the field trip. And the particular date is what time? 24? So the date that we travel to E-Tree is November 14th. E-Tree, and it's in Hsinchu. We may depart at, I guess, 8:30, or we get together at 8:30. We depart at 8:45. So get together, depart, and I expect arrival before 10. And I don't think we need to stay there for too much time, so maybe we finish by 11. Finish. Okay, and then maybe we go for lunch. Maybe we go for lunch. And then we may come back to Taiwan Tech, I guess by 1 p.m. I hope. I hope by 1 p.m. Yeah. Really? Yeah, I hope. So you need to decide whether you want to go or not. No, it's optional. If the time is not available for you, then don't worry. other questions? Okay. Good luck to the exam.